Good afternoon. Welcome to the UCLA Division of Physical Sciences webinar, The Science of Our Lives. My name is Miguel Garcia Garibay. I am a professor in the Department of Chemistry and Biochemistry, and I am also the Dean of the Division of Physical Sciences. Although we are not yet able to welcome you to our beautiful campus in Westwood, we are very excited to share with you some of the developments that are going on as our faculty and students continue their groundbreaking research during this pandemic, working both distantly and in their laboratories under the most stringent safety conditions. Today, we have three of our faculty sharing with us their perspectives on one of the most promising and exciting new developments in science and technology. We will hear about the impact of quantum computing. Our three speakers are members of the newly formed Center for Quantum Science and Engineering. The center brings together faculty and students from physics and astronomy, chemistry and biochemistry, mathematics, computer science, and electric and computing engineering. They are one of the leading groups in the world working at the frontiers of what will become the next great technological revolution. The first speaker is Professor Eric Hudson. Eric is one of the leaders of a team that recently won a major award from the National Science Foundation to address some of the scientific challenges that will need to be overcome in order to realize the full potential of quantum computing. Their ultimate goal is to design advanced large-scale quantum computers. Welcome to our webinar, Eric. The floor is yours.
Thank you, Miguel. And thanks to everyone out there for tuning in today. I hope to use my time to share with you some good news, and that is sort of the hope that we have for the impact of quantum computing on all of our lives. There are a couple things I hope that you take away from today. And I think the first one is something you maybe don't think about too often, but I think is very important to realize. And that is that information is physical. What do I mean by that? Well, if you have, I don't know, a Word document or a database or a childhood memory, that information is stored in a physical system. In the thumb drive or the hard drive of your computer, it's stored in some electronic system. In your brain, it's in the connections of your neurons. Now, because that information is embodied in a physical system, that means information processing is governed by physical laws. So whether you're, editing a Word document or calculating the spread of COVID-19 or just dreaming about what you're going to have for dinner tonight, that process is governed by physical laws, because at the end of the day, both in your brain and in the computer, these are electrical signals moving around, and the way electrons move is governed by physics. And that has some really important consequences, because our understanding of the universe, which is effectively what science is, tells us what is possible and what is impossible, what we should try and what we should leave alone. And Newton's equations, which are shown here, you ever think you've all heard the story of Isaac Newton sitting under the tree, the apple falls, and he has this epiphany and figures out gravity and everything about the universe. Summed up in this sort of famous equation, F equals ma, that a force on an object produces an acceleration, is basically how we understood the universe until very recently, actually. But in the early 20th century, Erwin Schrödinger came in and said, this F equals ma equation is only approximately true. And that in fact, a better description of the universe is given by something we now call Schrödinger's equation. The details of the equation aren't so important for today, but what is important is that Schrödinger's equation allows things to happen that Newton's equations do not, right? To put it another way, Schrödinger's equations reveal to us that the universe allows certain things to happen that we didn't think were possible before. I should define a little bit of jargon before moving on, because I'll use this a lot, and probably Clarice and Christopher will as well. When we say classical mechanics, what we're referring to is sort of the description of the universe that Newton gave us. The classical sort of indicates it's the old way of thinking. Mechanics is effectively the study of motion of things. What Schrödinger gave us, we call quantum mechanics. And here quantum refers to the fact that when you really drill down and look at the finest scales in nature, things are always quantized. They come in discrete bits. Okay, so what does it have to do with computing? Well, it turns out that quantum systems, some of these extra features they can have, make the computing of quantum properties much, much harder. And that's because they can be in these superposition states, and they can also be entangled with one another. And let me illustrate that to you with an example. Now imagine we have an electron. An electron is a subatomic particle that's in every atom. There are, an untold number of them in your body right now. Right? You may remember from your high school chemistry that each electron has a spin. Spin we can think of as effectively a little bar magnet that rides along with the electron, and it can point up or it can point down. And we might label those states 0 and 1. If it's pointing up, we'll call it 0. If it's pointing down, we'll call it 1. Now, if you think for a minute, you realize for this two electron system, there are 4 possible states, right? There's the opposite, where the first one's pointing down and the second one's pointing up. We might call that 1, 0. There's also the states where it's both pointing up, both pointing down, 0, 0, 1, 1. Now, these are what we like to call classical bits. Bit means binary digit. It basically just means something that is either on or off, 1 or 0. And at the end of the day, you can break all information down into bits. So if you can store 1s and 0s, you can store anything. And this is effectively how classical computers work. They're not exactly working with single electrons, but this is basically what they're doing. You have some memory, you put in 0, 0, 1, 1, or whatever to write some information. Now the difference with a quantum system is quantum systems can be in both the up and the down state at the same time. And they can also be correlated with other electrons. So that means that a quantum system isn't just going to be in one of these 4 states. It can actually be in all 4 at the same time. And this presents a little bit of problem for physicists. How do we label this? If we write it down as I've shown here as just 0, 0 plus 0, 1, so on, you might be tempted to add this up and get 22, and then you're confused about what this means. So you'll see me draw little lines around these numbers like this. And this is just our way of keeping track that this is labeling a state. Now what's important is that the system can be in any one of these 4 states. It can be in all of them at the same time. It can be in different ones with different weights. And so we really parameterize the quantum state by the following expression. Here, A1, A2, A3, and A4 are just numbers that indicate how much of the state is composed of the substate there. So if A1 was 1 and all the others were 0, then the state would just be 0, 0. But all the A's can be non-zero at once, and this can be some superposition and even an entangled state. And that's the key to quantum computing. Oh, I should mention, by the way, these are what we call quantum bits. It stands for qubits. When you hear the word qubit, that just stands for quantum bit, and it's just a quantum binary digit. So why is that important? Well, it turns out that the most important problems we face are really quantum problems. If you're like me, you've spent a lot of time worried about this little guy the last few months. Wouldn't it have been nice if, when it was first discovered in late 2019, that within a few minutes a computer was able to calculate everything about its properties, everything about how it works, design some sort of antibody that we could all go get, and then the coronavirus would just have been a sort of minor inconvenience where everybody needs to go to the doctor for a minute. Likewise, we're facing the human race really is facing really dire problems in terms of energy consumption. Wouldn't it be great if we could design materials for harvesting energy on our computers? Because we understand all of the physics, all of the chemistry that drive these things. It's just that we can't put them all in a computer and calculate it because it's just too hard for modern computers. And why is it too hard? Well, it's too hard for the reason we just saw. If you were paying attention, you notice we just had 2 electrons, but somehow we have to keep track of 4 numbers now. That's the sort of secret of quantum physics, is that the numbers, the amount of information you have to keep track of scales exponentially in particle size. So that if you go to just 300 electrons, and let me remind you that all of these things that I'm talking about, coronavirus and these antibodies and material science, contain much more electrons, right? Millions to even, 10 to some large number of electrons. But even at just 300 electrons, there are more terms in the expression to describe the state than there are atoms in the known universe. So even if I had a computer composed of every atom in the universe, and that atom was a bit, I couldn't even write down the state of the system to begin the calculation. And that is why these problems are basically unsolvable at the at the most correct level. However, a quantum computer only needs 300 qubits for this problem because it can be in all these states at once. And that is essentially the power that quantum computers bring to us. They're going to solve quantum problems. They're going to do other things too, but the thing I think that is most important is that they're going to solve these quantum problems. Okay, so what do quantum computers look like? Well, there's a lot of technology being developed right now. I'm just going to tell you about 3 that are sort of the main ones being done in industry and in most labs. Honeywell and IonQ are developing these atomic ion quantum computers. Here, individual atoms are isolated. You can sort of see in this artist's rendition, these little blue dots are atoms, and each atom is a quantum bit. Google, IBM, HRL, which is a local company, are developing what you might call artificial atoms. These are superconducting silicon qubits. These are nanofabricated devices which behave a lot like atoms and can store quantum information. When are these things going to be available? Well, already IBM, Google, Microsoft, IonQ, Honeywell, and Rigetti, all except for Microsoft, actually have quantum computers that you can access through cloud services. Now, in most cases, these things aren't more powerful than your laptop, although for certain problems, at least at Google, they've been able to show a calculation that can't even be done on the largest supercomputer in the world already. That said, despite all this good news and all this great industry investment, I mean, each of these companies is spending hundreds of millions of dollars a year on this. Despite all this, we're still years away from the quantum computer that can tackle this problem, for example, like the one that could have made coronavirus just a minor annoyance instead of the showstopper it's become. And why is that? Well, it's because quantum computing is hard. And the reason it's hard is there's 2 chief problems that we face. The first is that quantum objects are easily disturbed by their environment. And I'll give you an example. The Honeywell quantum computer is based on atomic ions. We do something very similar in our lab at UCLA. This is a picture of an experiment I work on in collaboration with Wes Campbell. Here we're trapping, I think it's 8, if you count, yeah, 1, 2, 3, 8 atoms. And this is an individual atom you're seeing here. And each atom is a quantum bit in this quantum computer. And so if we take the guy on the end and we put it in some superposition state, between 0 and 1, and we're getting ready to do some sort of quantum computation, if somebody gets in the south elevator of Knudsen Hall and goes up to the 6th floor, it just ruins it. Because that elevator is incredibly magnetic. They use really cheap steel in the counterweight. And whenever that thing goes up and down, it just screws up our quantum bit and it sort of erases its memory. So that's one problem, isolating these qubits from their environment, especially as you scale up. And the other is more technical. It's just that this is, if you walk into one of our labs, this is kind of what they look like. And this is for this 8 qubit system. We need to scale this up, 100-fold, even more. And we obviously can't build even 10 more of these. It would just take up too much space and cost too much money. So we need different engineering approaches to this. So as Miguel alluded to a couple years ago, we founded the UCLA Center for Quantum Science and Engineering. The purpose of the CQSE, as we call it, is to bring together engineers, computer scientists, mathematicians, physicists, and chemists to work together on these important problems. Because we really need these across-domain knowledge to solve these problems now. It's become too hard for one field. And we'll hear about that later from Clarice and Christopher, who are some of the newest members of the CQSE, about their exciting research. Now, what's some good news for us that Miguel alluded to, and you may have heard about, was that in late 2018, the National Quantum Initiative Act was passed into law. And despite everything going on, this was an incredibly bipartisan effort. You could see that the vote was actually 97% in favor. And it was actually introduced by Lamar Smith from Texas. And that's because both sides of the aisle agree that quantum science is important for the economic security of our country. And what the National Quantum Initiative does is it establishes about a little over $1 billion right now, hopefully more to come, to advance quantum information via coordinating research at all levels. But also it directed the National Science Foundation to establish institutes to lead the nation in the different quantum technologies. And if you happen to be on the UCLA newsroom mailing list, you may have got this nice article from Stuart Walpert late last month announcing that our center, along with some other UCs, UC Berkeley and UCSB, were selected to lead the NSF's premier quantum institute for quantum computing. So this is a really exciting time for us in California, and especially in Southern California, but really across the whole nation. Now this institute is going to do a lot of things, and I would love to talk to all of you about those linked if you have questions, but I wanted to highlight a couple of things, basically just to use my chance to speak to so many people to maybe make some connections. And I want to tell you about 3 things we're doing that I hope can have some impact in your life. The first is we're working very hard at coordinating industrial partnerships, especially in California and Southern California. So if you're out there listening from the area and you're in the tech industry and you're quantum adjacent or maybe even quantum centric, please reach out to us and let's talk about how we can all work together. The other is that if you're in SoCal in one of our communities, or if you're an educator in SoCal, we're working with a very serious outreach effort to bring people into the field. You'll hear me say this again if you're around me much at all. That is that there are just not enough people working in the quantum sciences. We don't even have enough people to really build the devices right now. So we're trying to bring in the best and the brightest, and we really want people from all backgrounds, all walks of life. That diversity of experience brings different problem-solving skills to us, and we need them all. The last thing I'll mention is sort of springboarding off of that, is that our most important resource is our students. So we're doing a couple of things through this institute. One of them is we're starting a new master's program in quantum science and technology that should be taking students in fall 2022. So if you're thinking about graduate work around this time, remember this will be the quickest way to get into the quantum field. That said, we're already training quantum scientists at the PhD level. All the people in my lab, that's what they're doing. All the people in Clarice's and Christopher's lab, it's the same thing. And I just want to remind you, because a lot of people maybe don't know this, that if you do a PhD in quantum science, in any science field, it's free. And not only is it free in the form of you're not paying tuition, we actually pay you a salary. Now we're able to do that because of grants and because of philanthropy from our partners at UCLA. And the reason we do it, even though it limits the number of people we can take, is we want you to be able to focus on your education, being in the lab, innovating. So if you're out there thinking about what to do with your life, consider quantum computing. And I want to end with sort of one thought, and this is basically, I think sums up the importance of this. This is the scientific adventure of our time. If we can build a quantum computer, it will alter the course of humanity. We're going to, problems like disease, energy, those are going to become much more solvable, maybe even not problems at all anymore. These quantum problems are really, really important. But we're not sure we're going to be able to get there. We think we know how to get there. It should be possible. We're not breaking any laws of the universe, but there are some serious technological challenges. And so we need help. So if you're interested in partnering with us in any way at outreach or coming into the lab and doing research, please reach out to me and I'd be happy to talk with you. Thank you very much.
Thank you very much, Eric. I think that was really exciting. I totally agree. This is absolutely one of the most exciting and intellectual endeavors of the future. And I think there's many opportunities and it's very exciting. So For our next presentation, we will have Professor Clarice Aiello from the Department of Electrical and Computer Engineering. Professor Aiello studies how quantum mechanical effects involving spin, which is one of the quintessential quantum properties of matter, might underlie biosensing phenomena such as magnetic field detection for field migration and other applications in biology. So welcome, Clarice. We're very excited to hear your presentation.
Yes, I'm excited as well. I have just started at UCLA last year, so I'm wearing the colors here. Can you all see me? Yes. Okay. So I like to call myself a quantum mechanic. This means that I'm trained as an experimentalist to build apparatuses to study and control those things that are so small and so well isolated from their environment that they're better described by the laws of quantum mechanics as opposed to the laws of classical mechanics that Eric discussed. So the first thing that I would like to do is like, welcome to the quantum world that you already inhabit. Okay, there are many, many things in our daily lives that are powered by the laws of quantum mechanics. I work in a field called quantum sensing, which is a sister science to quantum computing. And I'm going to start my story by telling you that I think that humankind is obsessed with measuring things better because it means that we understand them better. So we may think about measuring better frequencies with this very precise atomic clock that it uses quantum mechanical phenomena to function. One can think about measuring better magnetic fields so that the image of your baby is better resolved. This is actually a MRI, magnetic resonance image of a baby inside the mother's belly. And also, you might think about measuring better accelerations so that your gaming experience is enhanced. Those tiny accelerometers, they're present in all sorts of video game consoles and even your smartphone. But the question that I ask is, what happens if the quantity that you want to measure is very, very small? Worse, what happens if the object causing the quantity to be measured is very, very small? I'm going to argue that in this case, you need a tiny little sensor that is able to measure tiny little quantities. If this sensor is tiny, let's make it very, very tiny. Let's make it quantum. There's a whole body of mathematical arguments that they can prove that the fact of sensing a quantity with a quantum object improves your measurement. In other words, the sensor's quantumness enhances the measurement. And this is a feature that is also explored in quantum computing that Eric just beautifully described. And this is just a picture of, you might have seen it, of one of Google's quantum computers. Eric actually helped me here because next on my list would be to introduce two spins, right? Say the spin of an electron, which makes a simple quantum bit. And as Eric explained, a spin pointing up or a spin pointing down means just two different energy levels of this merely quantum property called spin. If the classical bit in your computer, right, can be thought of as zeros and ones, which just code two different, say, voltage levels in your computer, right? Say 0 voltage and 5 volts or something. A qubit, as Eric explained, is more like a tunable sort of button where you can have those qubits in superpositions of zeros and ones. And I'm sorry, I think you might be hearing the construction behind me. Okay, but we're back to quantum sensing. I'm going to show you really quick that a spin, a quantum object, a spin in an electron in diamond can be put to use as a very precise magnetic field sensor. And how does that work? That all sounds weird, right? So the spin of interest actually arises from a crystal defect that is found in the diamond lattice, really like the diamonds that you have in your rings, right? Some crystal defects in diamond, they absorb light and fluoresce, okay? And those lattice defects, they are responsible for the color of those nice diamonds that you see there. So the way we try to find those atomic defects that actually act like a spin in diamond is quite easy. We put a piece of diamond, it can be super crappy, like on top of a moving stage, okay? And we move it around at the same time that we shine laser light through a objective, so that we are actually shining light on top of a moving diamond sample. Okay? So I told you that this crystal defect absorbs light and then fluoresces, so that the moment where we hit one of our defects, that one defect is exactly below the objective, we expect to collect some light, okay? And that's exactly what we do, and you can see how this looks like at ever increasing scales. At the rightmost picture there, what you see is very impressive, because what you're actually seeing is the light or the fluorescence being emitted by a single spin in this material at room temperature, like diamond, right? So the defect itself that acts as a spin is way, way smaller than this, but you can still see its light signature, right? At about, say, at a very good resolution. What's super special about this particular defect, lattice defect or spinning diamond, is the fact that it has a, that's jargon, quantum state dependence fluorescence intensity. All that means is that by just looking at how strongly that blob is fluorescing there, you can actually tell if this spin is pointing up or if the spin is pointing down, which is absolutely remarkable. But I promised you that we could put this spin to work as a very sensitive quantum-based magnetometer. And that's how it works, right? Here, I am just depicting two states of this quantum spin, right? And for this particular system in diamond, their energy difference is in the microwave, is at the frequency of like in the same band as the wave emitted by your microwave in your kitchen. It turns out that one of these states, the one marked 0, doesn't care about external magnetic fields, which I call B here. Physicists usually call magnetic fields B. On the other hand, the uppermost state, called 1, is sensitive to magnetic fields. So that when this material, this defect inside the material is sees a magnetic field, effectively the 0 level does not care, whereas the +1 level, it gets shifted in energy by a tiny little amount that here I call delta. And it turns out that this amount delta is proportional to the strength of the magnetic field that is around this defect. So that, and that's super important, measuring a magnetic field is actually mapped onto the problem of measuring a tiny mismatch delta from a known energy difference, right? And I don't expect you to know this, but maybe if there are electrical engineers in the audience, measuring detunings or mismatches from a known energy difference, a known resonance, is something that engineers have known how to do for many, many decades. So this is how a quantum magnetometer would work. The big picture here would be then to have a tiny little probe that you could bring in very, very close proximity to your sample, so that you could maybe sense the magnetic field produced by one or a couple of nearby atoms. So that's the big picture on how you make a quantum magnetometer. Okay. I won't have time to talk about it, but my current work involves something very similar. Okay? In my past, in my training, I was used to working with those all technological sensors that you see there. But recently, I've realized that nature builds pretty good sensors too, right? And they're not necessarily quantum, but nature does a good engineering job, right? It has been practicing for many, many years, for millions of years. So one of the things that we're doing in our lab is investigating the possibility that very similar quantum properties, very similar properties to the spin in diamond, might be used by organisms to sense, to interact with their environment. One hypothesis, for instance, is that when birds migrate, it's known that they migrate following, at least as a partial cue, the magnetic field of the Earth, which is like smaller than the magnetic field like of your phone when you hold it this close to your ear, right? So how do they do this? It's known that they sense the magnetic field of the Earth to migrate, at least to some extent. One theory is that they do so by employing very simple quantum properties akin to the quantum sensor that I just described in diamond. So we're building high-tech experiments in order to investigate potential quantum mechanical effects in biological systems. Okay, so this, I'm leading this lab that is concerned then with quantum effects at room temperature in noisy environments. Feel free to, again, to contact me, contact us about opportunities and to hear more about what we're doing. And I would like to finally invite you to join the quantum, okay? So we're organizing during fall semester a online seminar that is called My Favorite Qubit, or Quantum Computing as Told by Leading Practitioners, in which for 10 weeks, we're going to give very brief introductions on quantum mechanics and quantum computing. And afterwards, specialists of different qubit implementations, as Eric showed in the past, they will present why they chose to work with their particular chosen qubit. Okay, so register now. The site is there. And another thing that I'm involved with, and I'm very excited, is trying to engage a diverse, inclusive undergraduate population into the quantum sciences, right? So currently the WE at UCLA, WE stands for Women in Engineering. They have technical academies where students meet either presentially or online to do some hands-on projects on that particular technical academy. And industry people, they come, they help the students develop those little demos. And right now we have a semiconductor academy and a aerospace academy. And what we're trying to do now is to get a way to put a quantum academy in place. Okay, so I think that's all I wanted to tell you, and may the quantum be with you.
Thank you so much, Clarice. That was really, really interesting. So exciting to think how, you know, quantum phenomena and quantum sensing may play a role in biological process, in some of the things that we do, you know, to interface with the rest of the world. So thank you again. Now, the final presentation will be by Professor Christopher Gutierrez. Professor Gutierrez is one of the brightest young physicists in the United States, and we are very lucky to have him now as the newest member of the Department of Physics and Astronomy. Christopher works on the creation, design, and atomic scale visualization of very unusual states in quantum materials. Christopher, welcome to UCLA.
Thanks, Miguel. And thanks everyone for attending. So what I'll be talking about today is imaging and designing the quantum world. And so what I want to do is to take a step back and let's think about computation itself. It's actually interdisciplinary. It takes several different groups to come together to even come up with the classical computers that we have today. So an example on the left here, I have a picture of the very first transistor that was created in 1947. So this object can fit in the palm of your hand. But now we look at the transistors that are in the middle. So if we all have a smartphone with us right now, Actually, that transistor that fit in our palm of our hand in the 1950s, now we have 8.5 billion transistors in just one smartphone. So what I want to stress is that, what Eric showed was that there's different very mature platforms for qubits, ions, superconducting junctions. But what is the next generation qubit? And what I want to stress is that all the work that came about from the very first transistor came about from basic fundamental research on semiconductors and looking at those materials. So although I am what Eric called quantum adjacent, it's still crucial for looking at new materials to see what is going to be the next generation technology. What is it going to be based on? What materials? So actually, I do research on what are called quantum materials. So what are those? Those are materials where you have emergent quantum properties at the big human scale. So what we're used to learning is that quantum effects are only at the very, very small. But actually, you have these really cool and interesting materials. Like this one, we have a high temperature superconductor. And what you see there is that when that high TC superconductor is placed above a magnet, it actually levitates. Now that you saw from the size of the tweezers, that's a big piece of material. And yet the physics that describes why it levitates over that magnet is purely quantum mechanical. And actually it's due to a huge millions and millions of electrons that are in a highly entangled state actually creating that. So quantum mechanics isn't always just at the small scale, it can be in these big things, which is what quantum materials are. Now another quantum material that I'll be talking about in this talk is graphene. You might have heard of it. So graphene is graphite, the graphite that we actually draw with in our pencils. And it's actually created by using Scotch tape here on the left. We actually use Scotch tape and we exfoliate single layers of graphite. Now the interesting thing is that all the electrons that are inside of graphene, because they're forced to move within a single layer in this honeycomb pattern, the electrons actually have these really interesting properties. They behave as if they have no mass at all, which is very strange. Also, the graphene is one of the strongest materials that we have. And so all of these properties come from quantum effects that we actually can experience at the human scale. So one interest that I have, and this is related to what Clarice was pointing to, is that we usually think of defects as something that's bad. But actually what me and Clarice both find interesting is that there's ways to actually use defects for positive benefits, for actually changing things. So actually one thing that I'm interested in is using crystal defects to change the properties of quantum materials, to actually tune them to create new functionalities. So one thing on the left is depositing defects on the surface of materials to create new phases of matter, or giving voltage pulses to the surface to actually design artificial atoms, or to take two layers of a quantum material and twist them and to create all new phases of matter. So the one I'll be focusing on here is this one in the middle, an artificial atom. So first I want to acknowledge the collaborators. So this was done with previous work when I was at NIST, the National Institute for Standards and Technology, in the group of Joe Strosio. All right, let's take a step back. So, how can you create an atom? The atoms that we know about so far, they come from the center of stars. All of us are made of star stuff. And the experiments that Eric and Wes and the other groups at UCLA work on, those are actual atoms that come from the ground. They come from Earth. What I'm going to show is that we can actually use these 2D materials to actually design artificial atoms. So what do I mean by an artificial atom? So the other word that we call them are quantum dots. So if we think about a regular atom, the regular atom, its structure is described by having electrons that are trapped in a Coulomb potential due to the nucleus, due to the protons here. Now, in a quantum dot, instead, we have this big structure, right? It can be from 10 times the size of an atom to up to 1,000 times larger. And yet, the electrons are still confined to some space. And so what that does is, just like in a regular atom, due to this confinement, the energies are discrete. So this is what Eric was talking about, that, you know, this is the emission signal for a helium atom. It only gives off certain types of energies. You know, there's no other energies in between. Well, in these big artificial quantum dots, we have the same thing. Its energy structure, which we see through transport measurements, it only has discrete values. So what's really interesting is that we can take an object that is 1,000 times larger than a regular atom, but it still behaves like it's one giant atom. So what I'm going to show is how we can actually print quantum dots using graphene. And so I want to compare this with the way that other quantum dots have been made. So quantum dots are one platform for creating a quantum computing qubit. And so at UCLA, the Zheng group uses different platforms. One of them is through silicon and silicon germanium. And so these quantum dots are about 100 nanometers. And these are made through really advanced nano fabrication techniques. So actually what they have here are 3 different quantum dots that are coupled. What I'll show is that we can use a sharp tip to actually zap the surface and create a quantum dot, as if you were just, you know, printing with, like a tattoo needle. So I want to stress that this method for doing this was developed first at Berkeley, and then we used it at NIST. And now 2 of us that were both at these 2 institutions now have our own groups at UC Santa Cruz and UCLA to continue this nice work. So how does it work? So if we bring the tip close to the surface, we look at this structure that we have of boron nitride, which is blue, and graphene. So the boron nitride has these natural defects inside of it. So if we bring our tip close to the surface and give it a voltage zap, that actually freezes in this potential in the surface that's going to trap electrons. Now, what this is used to is one of my favorite toys when I was a kid was the Magnadoodle. I don't know if hopefully everyone knows what this toy is, but if you've ever cracked one open, which is what I did when I was a kid, it works actually similarly. So you have this stylus with a magnetic tip at the surface. When you bring it close to the drawing pad, there's these magnetic filaments inside of the gel that actually get attracted to the tip, and it lets you design any type of figure that you want. So similarly, we're doing this, but at the nano scale, using the natural defects that are in boron nitride. So how are we going to probe? How are we going to measure these things? So I first want to describe quantum tunneling, which is one measurement tool that we use in my group. So with a classical object, if you throw it at a wall, you're going to have some reflection. You know, this is something that we're used to. Now with a quantum object, you know, such as an electron, you can launch it at a barrier, and then sometimes it'll reflect back at you. But the really interesting thing with quantum objects, there's a very small probability that it goes right through the wall. This is something that we're not used to in the classical world. So you can imagine that if you put 2 pieces of metal together, you put a voltage across them, there's a really small chance that an electron on one side will quantum tunnel to the other side. Now, because that probability is low, depending on this barrier or the distance between these 2 electrodes, that tunnel current is really small. It's 100 picoamps. So to give you some reference, the electrical current in your refrigerator right now at home is 6 amps, or it's 60 billion times larger. But we can actually measure this tunneling current. So what we can do is that we can actually visualize, we can actually see electrons. So one way to understand it is that we bring our tip close to a surface. And if you're at home right now, if you just dragged your finger, drag your pointer finger across your left hand, you know, you can feel the bumps of your finger. So that's exactly what we do with a sharp tip. We actually can measure that tunneling current, and we use computers to tell that tip that can measure the height of the tip as it rasters across, and we get these beautiful atomic images of the surface. So this is the surface of graphene. This is when the tip is low, it's dark. When it's high, it's bright. And if we zoom in, what we see is that we can actually see the atoms. So this is the atomic structure of graphene here. And notice that it's dark where there are no atoms. So we can actually see the quantum world. We're making the quantum world big. Now, another really powerful method is to actually look at those quantum dot states, those artificial atom states, and that's to use tunneling spectroscopy. So spectroscopy means energy structure. So you can imagine we do these tunneling experiments at different voltages, and we can stack up our images into this, really dense set of images. And if we slice through this data set, just like you would a cake, we can find out where are the electrons at different energies. So if we slice our cake this way, we would see that all our electrons at this particular energy have this particular pattern in real space. So what we're looking at here, this is actual data. These are electrons behaving as waves inside of this quantum dot. Now, if we slice our cake the other way, we can now look at where the electrons are as a function of energy now. So before we're looking at one single energy, now these are at different energies. And this is exactly what we had expected for an artificial atom. We can see that at different energies, the electrons live, they don't have energies in between. So the energy is discretized. So we've actually created an artificial atom, and we're able to actually look at it, something that you can't do with regular atoms. And to me, the coolest thing is that, if we now do these, slices at any particular energy, we can compare them to the atomic states that we would imagine from chemistry. So, if we look at the n=1 state, we look at the hydrogen state, we notice that it's just one single blob with no nodes. If we look at the second atomic state, we see a ring in the middle. And for the third atomic state, we see now 2 rings. So simulating quantum nature, but we're doing it with absolute control over the surface, and we get to image it. So what do we do after we create that quantum dot? Well, now remember, what we want to do is really control the quantum world. So what we found in these papers that we published with my old group is that with small magnetic fields, we can have really finely tuned those quantum dot energy levels. We can actually control where the electrons are and what energy they have. So notice that before, all of the electron energy levels are closely spaced, but as we start to increase the magnetic field, we start to separate them out. So we can pick out where the electrons are and with what energy. So some of the next steps are to continue some of this quantum dot work, and hopefully that it has some bearing when it comes to computation. What I want everyone to take away is that quantum materials are a really interesting platform for designing never before seen states. And so I want to just finish by saying that, who is going to have the next breakthrough? Who are going to be our quantum scientists of tomorrow? UCLA is located in one of the most diverse cities in the world. And the next quantum, scientist is in our backyard. It's in our neighborhoods right now. And I know because I'm from South Central Los Angeles, and there's a huge talent pool there. And so one thing that I'm really excited about to join is being a part of training the next generation of quantum scientists and fulfilling UCLA's mission of education, research, and service. Thank you.
Thank you, Christopher. That is really exciting. So again, thanks to Eric, Clarice, and Christopher for giving us some idea of all the exciting things that are going on in the world of quantum and quantum computing. So I think we have an opportunity to have our speakers address some of the questions from our audience. So let me see, I think I'm gonna look at the QA section, and I believe the first question might be addressed to Eric Hudson. It is from Nikhil Bardwaja, and it reads, when you read that one bit, how do you ensure that one bit does not change for future calculations? Can you answer that, Eric?
So in a quantum computer, you can't. This is the idea of the wave function collapse. If you've heard of sort of the Schrodinger cat analogy made to sort of demonstrate sort of the oddities of quantum mechanics. So if you have one of these states, these superposition states I showed you that are sort of 0 plus 1, when you measure, you either get 0 or 1, and you erase that superposition. And that is why quantum error correction is very hard. So that's a buzzword, or not a buzzword, that's a big word. You know, in your normal computer, there's all sorts of error correction. Like if I send a file to you, your computer has ways to check to see if that was done correctly without any errors. In a quantum computer, since you can't look at it, how do you know if you made an error or not? And so to me, quantum error correction is one of the most fascinating topics of it all. That's a little bit beyond this webinar, but I'd be happy to talk about that offline.
Excellent. Oh, wait a minute. Let me see here. I'm trying to get my screen back. Okay, here it is. So let me, I think that the next question actually you already addressed. It was from Len Weisberg, and I think it's exactly about, you know, the fact that reading the information destroys the information, and I think that's a really good one. I have another question from Eric from Eva Liuponute. How did you choose trapped ion qubits as the main quantum technology to focus on?
Yeah, so it's a very interesting question. There's lots of things to deliberate. No one knows the right answer, obviously. Although, you know, in 20 years we'll say, oh, it was obvious. Right now, no one knows. So trapped ions, to me, have several properties that I think are important. The biggest is that every atom in the universe of a certain type, like we use a certain flavor of barium, if you will, barium-133. Every barium atom in the universe is identical. And so that means each qubit is identical. That makes it easier for them to talk to each other. It's easier for them to control. Now, one of the challenges that come with trapped ions is how do you scale these things up? Because you need lots of them. The other technologies like superconducting qubits, the reason Google and IBM have gone for them is they kind of look like computers, right? We know how to nanofabricate stuff. And so I can build a lot of these up, control them with electrical wires. But in the end, they have some disadvantages. I like to say they have hair, like because they're man-made, each one's a little different. And so the communication is a problem. There are long-range crosstalk problems with them. And you just don't have that with ions. So I obviously have decided that I think ions are the way forward. But that's not to say that maybe those technologies won't be the winner or other technologies as well.
Great, thank you, Eric. Let's see, this could be for any one of you. Any comment about today's announcement by Amazon Web Services about opening its amazing bracket computing platform as a launchpad for people to explore quantum computing? So that means that just about anyone will be able to do quantum computing, right?
Right. Yeah. So I don't want to be the only one talking, but I will just say, I think it's really exciting. IBM has a very similar thing and has had it for a while. That gives you really hardware access. Google, to a lesser extent, Google is more with academic partners. But all these companies are doing this for several reasons. But one of them is they're hoping to drive interest and to get more people working on it to figure out what can we actually do with a quantum computer, because that might be the most exciting thing, is that we don't really think, we understand programming like regular programming as humans. It's very natural to logical thought. Quantum computing programming is different, and we need to learn how to do it. And so I think that's the really exciting thing about it being open to a lot of people.
Yeah, so that was just recently, Eric, the Qiskit initiative, which was, yeah, a lot of students have joined, and looks really interesting, trying to get people to just think about how to program for a quantum computer.
Oh, that's exciting. So this is another question for all the panelists. So quantum computing will solve many problems that have existed for some time. So the question is, what problems might it create that haven't existed before?
I want to have a stab on that. Well, I'm not sure it's going to create a problem, but I think that everyone is going to have to start being mindful about the power of quantum computers, right? What does it mean if one nation has control over quantum computers, whereas the others don't, right? What does it mean in terms of security right? I don't know. What do you guys think, Eric and Christopher?
I think it's like any technology, right? Look at the internet. It can be used for for amazing things. At your fingertips, you can learn anything you want on YouTube, but it can also be used for bad things. But you're right, for geopolitical concerns, quantum computing. Yeah, I think.
Great, thank you. Here's another tough questions, but this is actually very constructive. And that's also for all panelists. So what skills and aptitudes should a person have if they want to become a quantum scientist? What strengths and interests make a student successful in this field?
Creativity.
Creativity.
Enthusiasm.
Tenacity.
Creativity, enthusiasm, and tenacity.
Yeah.
What that just about describes every UCLA student.
Yeah.
Fantastic.
Yeah, I just to piggyback, so what Eric was saying, I think what students also don't know, when we tell them that PhDs are free, is also how much creativity comes into being a scientist. It's not about reading a book and doing something. You're at the forefront. You're creating new knowledge. So you're in the lab and you get to, you have awesome colleagues and collaborators, and it's much more collaborative than students, I think, really know.
Mm-hmm. Excellent. So to follow up on that, a train of questions. So what resources could help us more quickly attain the future potential of quantum computing? What are the resources? So, what is it? What are the key elements that will help us break through?
For us, I would say that it's what Christopher just said. It's students. The ability to have more people in the lab working is really what it comes down to. There just aren't enough people that are able to do this yet. We just can't support enough people. So ways to get more people in the lab, I think, is what I need anyway.
Right. That makes a lot of sense. So if this is going to be the technology of the future, I think it should be very appealing for students to be engaged on that. Here is another question. And I guess this can also be addressed to all of the panelists. And it reads, quantum computing is such a profound development that it may still be difficult to grasp. Even after your enlightening presentations, what historic scientific innovation can you compare it to so that non-scientists might be able to appreciate?
That's a great question.
Right. Huh.
Clarice, you unmuted yourself.
Maybe the invention of the transistor?
Yeah, I mean, when I was putting together this talk, that's what I was thinking a lot about. It was this ugly thing. You look at that photo, it fits in the palm of your hand. And now, what is it? Something like 70 years later. And yeah. And actually, that was pure germanium. They moved to silicon later, so they didn't know which was going to be the right thing, right? Transistors supplanted vacuum tubes. So it's a little bit similar to the qubit idea. Which is the one that's going to win? Or is it going to be a mixture, some hybrids of qubits?
And the ENIAC, like those very, very old computers used to be as large as the labs that Eric showed and the big Google quantum computer. So maybe in a couple of centuries, we might have a quantum laptop or something. No pressure, Eric, no pressure.
I don't want to take a stab at this too, Miguel, because I actually think that there's nothing in history to compare it to. Because the thing is, like, all these things that we think are hard, like, designing new drugs, designing new materials, understanding biology, we understand all of the physics, all of the chemistry behind it perfectly, but we can't do it in a computer because it's just too hard. If we could calculate all this stuff in a computer, years and years of lab work could be reduced to however it takes to run that code. And, if you could design medicines for a person within a few minutes, I mean, think about what personalized medicine like that could do. So I'm maybe, too much of an optimist, but I think that really there's nothing that we've seen as a species can compare to what this could do.
Mhm.
And Eric, maybe as a point of comparison, can you tell us like what's the state of the art in, say, number of qubits in a quantum computer that people have?
Yeah, so I mean, mostly it's in the 50 to 100 range right now. And we need, factors of 10 on top of that to really get to for the problems I'm talking about. Now, there are already applications that you could make money with a quantum computer. One of those being verifiable random numbers. It turns out people will pay you for truly random numbers. Most of those people are casinos, but they will pay for it. And a quantum computer can make random numbers that you can verify are truly random. So there are niche applications, but that's why we're years away, I think, from what.
Yeah. Thank you. So this is really, really interesting, but I think we are running out of time. So what I'd like to do is maybe give each of you, maybe half a minute or whatever to tell us your last thoughts about it. So what would you add that you think might be interesting to our audience? Oh, why don't we start with you, Eric, and we go in the same order.
Well, I think I'll just end with the same thing I said at the end of my talk, is that, the promise of quantum computing is immense, but it's not certain that we'll get there.
Mm-hmm.
We don't know of any reason we can't right now. We just need more people working on it. And if you're out there and you're looking for an interesting field, or you want to come partner with us, please reach out to us, because I think if we all work on this together, we can really move the ball forward.
Right. So Clarice.
Yeah, I'll second that. Please talk to us and contact us. And yes, quantum permeates our lives. So it's a promising field, and you just need to be, enthusiastic, have tenacity, and be creative, right? I mean.
Thank you, Clarice. Christopher.
Yeah, and I would also stress, from the very first slide, which is, you never know where basic research will take you. And so, since I'm quantum adjacent, and I'm looking at what kind of new physics we can see inside of materials and how we can manipulate those materials. And so, just basic fundamental research is always crucial.
Well, I want to thank all three of you for for your presentations today. This is a field that is fascinating, and we will be hearing much more about that. And hopefully, thanks to you, we'll see the field progress faster, and we'll make sure that our country has the workforce that is needed to really be competitive and really break through. So thank you all, and I want to thank everybody who joined us today. So we are excited to have you, and please join us for the next webinar, and come visit us. Send us an email. We will love to interact with all of you. So we'll see you next time. Go Bruins! Bye.